Hello everyone, welcome to the chapter 3, section 3.4, which is about three-dimensional force systems. So I hope you all look into the two-dimensional force system, and I hope you were able to draw the free body diagram and find the unknown forces. And also I have uploaded some practice questions which will be an additional information or some additional practice for the chapter 3.1 to 3.3 sections. So let's look into the three-dimensional force system. So from this chapter, the students will be able to solve the 3D equilibrium problems by drawing a free body diagram and then applying the scalar equations of equilibrium. So we know that when a particle is in equilibrium, the vector sum of all the forces that is acting on it, it must be zero. So the additional of all the forces should be zero. So that's what we look into our 2D equilibrium of forces. So all the forces in the x direction should be equal to zero, and all the forces in y direction should be equal to zero, and addition of the forces in x and y direction should be equal to zero. So this equation can be written in terms of x and y z components for 3D equilibrium. So we can write it as the addition of x component, y component plus z component is equal to zero. That means alone this should be equal to zero, and that should be equal to zero, and this should be equal to zero. So in alone, all the forces in all the directions should be equal to zero, and on the whole, these addition of all these direction also should be equal to zero for the particle to be in equilibrium. So this vector equation will be satisfied when your x is equal to 0, y equals 0, and z is equal to 0. That's what we looked into before. So the application, so most of the problems in our world is going to be 3D. So if you look into a system as shown here, the weight of the electromagnet and its load, so we need to know what are the forces that are acting on this chain so that we can take this, so that the assembly can be in equilibrium, so there's no any damage, so that's safe to take the objects, right? So we need to know the forces acting in B, C, D. What are the forces? So let's look into the equations of 3D equilibrium. So when a particle is in equilibrium, we know that vector sum of all the forces acting on it must be zero. Thus theta should be zero. So this equation can be written in terms of x and y, which we looked before. So this vector equation will be satisfied when all the individual should be zero. So you should be very careful about that. So these equations are the three scalar equations of equilibrium. So they are valid for any point in equilibrium and allow you to solve to like three unknowns. So previously for 2D problems, we had two unknowns and then we had two equations so we can find the forces. Here we'll be dealing with three directions, so we get three equations, so we get three, or if you have three unknowns, you should be able to find them. So let's look into the example one. So before moving into the examples or moving into 3D section, make sure you are clear with 2D and you know how to resolve the forces in X and Y direction, and you are perfect with that. And also please go and look back the chapter 2 to see how to resolve the forces, how to get the components in particular direction. So they are asked to find out the tensions in the cable AB, AC, and AD. So what's our plan over here? How do we solve this problem? First, what do we do is that we draw the free body diagram at the point A, because that's the common point to all the codes or the cables. Then we're going to write the unknown cable forces. That's going to be in TB, TC, TD in the Cartesian vector form. You can ask why I'm representing them as TB and not FB. It's good practice to note them as FB, FC, and FD, because in future, when we study trusses, which is very important, you will be studying that. You need that for the mechanics of material and other chapters. So when you are studying that, it's better to mark them by the forces because we don't know whether the forces is going to be tension or compression. So we always may mark it as force, and then we, after solving, when the sign comes positive, we say that as tension. When the sign comes negative, we say as compression. So in my case, I'm assuming them to be tension. So I say that everything has to be in tension. So when I solve, if I get a negative answer for some answers, so if I say I get negative for TB, then I say that's will be opposite to tension, so that's going to be compression. So you can mark it by forces or you can put it with tension, it's up to you. So once we got the unknown, we are going to write the equilibrium equations, then we are going to solve for them. So let's look into that. So first, so if I see my figure over here, so let's take my TB. It's already only acting in one direction, that is my X direction. So it's only one component in the X direction. So that's why we have TBI. So that's the X component. And let's look into my TC. And TC, I think you would be familiar with this because we all, in chapter 2, we looked into the exact same problem, how to get its component. So this is the TC. So if I get T cos 60, I will get this component. Then after getting T cos 60, then I get the T cos 30 to get the Y component. So that's what we have, cos 30 and cos 60. So if I get T cos 60 and if I get the T sin 60, I will get the Z component. And if I get T cos 60, and then if I get T sin 60, then I'll get the negative direction of my X component. So that's why we have the negative of X direction. That's my TC component. Then let's look into the TD component. So for TD, if I look carefully, they have given me the Cartesian direction angle. So sorry, the coordinate direction angle. So that's mean my alpha is going to be 120, which is mixed with x-axis, and my beta is going to be 60 degrees, which is mixed with y, and my gamma is going to be 45 degrees, which is mixed with z. So I have the component angles of that. So I know that if I know the angles, I can directly go ahead and then make the cos of that. So the XTD cos 20 and why it's negative, because it's the component of that is making with the negative y-axis. So when I get the component, it's going to be the opposite of my y-axis. So that's why I have negative. Then cos of my 45 for the vertical direction. And is that all the forces acting on my point A? Is that only the cables? No, I have a weight over here, which is of 300 pounds. So that's only a Z component acting over there. So now I have written my all equations and I know the equation. So I have like 4 equations. This is the components of all the forces acting. So now I'm going to write the equations of equilibrium in each directions. So first let's apply in the resultant. So we know that the resultant means addition of all the forces should be equal to 0. So that's, I know that. So once I know that, I'll take the X component equal to 0. Then I get Y component equal to 0. And then I get the addition of all the Z components equals to 0. So when I write that, I get 3 equations. So I have a I, J, K components. Now I can solve these equations and get this. So you have to use your algebra for solving this. You can use any way to use that. So first I will see which is easy to use. So here I can get a relationship between TC and TD. I can say that TC is equals to 0.5 TD divided by 0.433. And if I look here, I have only the equation with TC and TD, and from my previous equation, I know TC. I substitute that there, and then I can find my TD. Once I find TD, I go here and put and find TC. If I know TC and TD, then I find my TB. So this is the one way you can approach the problem. And then if I find my forces, I find like TC is equals to 203 pounds and TD is equals to 176 pounds and TB is equals to 139 pounds. So give yourself some time, and after this lecture is over, you can practice it on your own and see whether you get the same answer. So let's look into the example 2. So you have given a 600 Newton load, which is supported by 3 cords with the geometry which is shown here. So the cords are connecting A, B, A, C, and AD. So they're asked to find out the tension in the cord A, B, A, C, and AD. So what's our plan? Think about the plan. Yes, we know we are going to draw the free body diagram at A, and we are going to know get the unknown magnitude of F, B, F, C, and F, D. Then we are going to represent each form in Cartesian vector form. Then we are going to apply equilibrium of equations. So as I mentioned before, I said we can mention as F also, rather than having T, we can put F2. So give yourself some time, pause the video and try the problem on your own and come back. If you are stuck at some point, or if you think you cannot proceed, then come back to the video and look at the video, or else if you think you can do it and you can proceed, finish it and check for it. And once you do and then check, it will give you a better understanding rather than looking at the video, how the process is done. Okay, I hope you draw it on your own. So let's draw the free body diagram at A. And now I'm going to get the components of that. So let's look at FB. So if I see FB, it's kind of in my, what I say, XY plane. So it's make 30 with a Y. So I know if I get the cos 30, I get the Y component. If I get sine 30, I get my X component. That way I get my FB. And FC is simple. It's just in the opposite direction of my X. So that's the minus FC. And let's look into FD. So FD is a little bit different because here we had to get the position vector because the position of FD is given, which let's say 1 in the X and 2 in the Y and 2 in the Z. So if I get the position vector, you know, if you get the position vector of, let's say 80, then I had to get the unit vector to get the force. So my force magnitude is FD. So that's what we hear. So you can directly use that here and get the FD components. Now let's look into now let's equate the forces to 0. And then you should be able to solve. So from third equation, we can directly get my FD, then substitute here and get B, and then from the first equation to get C, and then gives you the values. I hope you get this close answer, or maybe you did halfway through or quarter way through correctly. Maybe your approach was correct. I hope maybe you would be little stuck at the position vector thing. So let's say that if for some forces, no angles or it's not lying in any direction, but only the position is given or where it locates, then you should be immediately know that, okay, so they have given the position. So I had to get the position vector, then get the unit vector, then get my force in that direction. Let's look into the another problem. So we have a 400-pound crate, which is supported by 2 cables, and let's say it's in equilibrium, and we have a strut at 80. So the magnitude of they're asked to find you the magnitude of the tension in each of the cables and the force that is developed along the strut 80. What's our plan? Simple. Just draw the free body diagram at A. Then we are going to represent all the Cartesian vector form in the vector form, and then we're going to apply it equal to 0. So as I mentioned before, pause the video, do it on your own, and then you can come back and check the answers. So this type of problems are already in the chapter 2. So you should be able to do that fast. I hope you're in the correct track, and I hope you are here to check the answers. Let's see. So my free body diagram. So you don't need, it's just to the stage. So FB, FC, FD, it's easy for you to show it in here near the A. So free body diagram is kind of the portion over here. You don't need to go up to here. So it's just here. So let's look into the weight. So weight is minus 400K down. So let's look into the FB. So FB, you know, here no angles is given, all the positions are given. So again, you had to get the position vector. So B is located minus 4 and minus 12 and plus 3. So how did that come? So we know that it's RAB. So it's going to be RB minus, So it's RAB. So we know that it's going to be RB minus RA. So what are my coordinates of B? So B, if I see my X coordinates, it's 2. And then my A is kind of located, let's see. So my B is in negative 2. So it's on the negative direction of X, and my A is also in 2, which is aligned on the same thing. So minus, but it's in the plus 2 if you look carefully. So that's equals to minus 4. That's for the I component. And let's look into the J component. So for my J, my B is in 4. It's going 4 from there. And my A is in 2.5. So that will give me, so a little correction over here. So if you look at the position of B, so as I mentioned before, so our AB, it's going to be RB minus RA. And where's my RB is located? It's -2 in that direction. So -2 minus A is in my X, so it's C. So it's -2I. And how about J? So for the J, my X is kind of in the Y for, sorry, for the B, it's on the Y, so 0 minus and 6. So that's equals to -6J. And my Z is going to be where it is. So it's 4 minus 2.5. So that's equals to 1.5K. Oh, because for the easiness to get a whole number, it's multiplied by 2. So everything is multiplied over here by 2. So that's why it's a little different over here. So everything is multiplied by 2 because this one will take into care the multiplication. So it's not going to be any matter. So that's not a problem. So you'll get the same answer if you use that too. So a similar thing we can do for C. So if I want to do for C, so our AC is going to be RC minus RA. So let's see the I component. My C is in +2 and my A is in already in the Z. So that's 2I. And let's look at the Y component. So Z is in the x-axis, so 0 minus, this is in 6, so that's equals to -6J. And let's see, look into the Z component. So my C is 5.5 minus this is 2.5, so that's equals to 3K. So it's the same here. Let's look into the R. So that's for the C. Now let's look into for the next one. So that's going to be our RD. So let's write for that too. So my RAD is equals to RD minus RA. RD, it's going to be in 0. So my X is 0. And then my Y for the A, my X is equals to 6. Hold on. Okay, so 0 for A. This is also 0. So that's equal to 0I. Then my J component. So JD is also 0. And this one is 6. So 6J. So that's -6J. And my Z component, D is 0. And my A is 2.5. So that's equals to -2.5. So that's the same thing over here, but here we have multiplied by -2, but that's going to be the same one. So if I get it, I'll get the equations written, and then I'm going to be getting my forces. Okay, so solving that, I get the forces. So this is an additional problem for you to solve. So we have if cable AD is tightened by a turnbuckle and develops a tension of 1,300, so the tension here is already given. So you know the tension in AD, that's 1,300. So they asked to find out the tension developed in AB and AC along the point. So this is simple. So you can give a try and go back to the slides and see the solution for that. And if you have any questions, please let me know.